All right, for the linear regression with coded data, you're going to use some of the tools that we just did in the last lesson where you make a spreadsheet, find the linear regression equation, and use your calculator to figure out what the correlation coefficient is, or the R. All right, so the first one here, uh, they give you the hot dog sales and for a Major League Baseball team. He orders food for the concession stands in order to determine the number of hot dogs that he needs to order for the next game. He examines data from 6 previous games, and he decides that the expected number of hot dogs sold at a game can be predicted from the advance ticket sales. The data shows the number of advance tickets sold and the number of hot dogs purchased. So right here, he's trying to figure out how many he needs to buy. Construct a scatter plot for the data and label the axes. Well, I know it's got a picture of a scatter plot here. It would be so much easier if you just opened a new tab and made another blank spreadsheet, just like we did on the last lesson. All right, so I'm going to type in the data. This would be the X. This row here would be the Y. And I'll pause that while I type in the data, but you just put in the data. So 45, 64, 37, 45, 64, 37, and so on. And I'll pause it while I type the rest of it in. All right, so now I've typed in the data, just like it looks here. Just typed in these numbers in here. Now I highlight the data, insert a chart. I want to make it a scatter chart. So I'm going to go over here and I'm going to make it scatter. Okay, and like I said, it plots all the points for you. This one goes from 0 to 30 and then by 40, 50, 60. So I'm going to customize it over here just like we did the other day. So that way we're not making a misleading graph. And I'm going to click the horizontal. This over here. And go right here for the minimum value. I want to put 0 and the maximum value. What was the maximum value? 64, so let's go to 70. 70. And it makes the scatter plot look more spaced out right. All right, so now I could do the same thing for the vertical axis. We'll just say it starts at 0 and goes to, so the y's go to 46, so we'll go to 50. 50. All right. All right, so I go up here to where it says series, just like we did the last lesson. I click the trend line, and then I'm going to go a little further where it says label, and I'm going to use equation. So now I've got it here, and I think, let's see what, construct a scatter plot and label the axes. Now I have not labeled the axes yet. So if I go back to the horizontal axis, let's see, maybe it's up here, oh, right, chart and axis titles. So here's where I'm going to label it. I'm not going to label the chart title, even though I probably should. I'm going to label the horizontal axis title. And so the horizontal axis is the X's here. And the X's are the ticket sales in thousands. So that's what I'm going to write right here. Ticket sales in thousands. All right, and if you notice, it automatically puts it down here for you. All right, now I want to do the vertical axis title. So I'm going to switch it to the vertical axis title right here in the same spot. The vertical axis was the hot dogs sold in thousands. So I'm going to put hot dogs sold in thousands. and it automatically puts it over there. All right, so I just made a graph. I've got the linear regression equation. Now, the reason I went ahead and put the linear regression equation is because I'm pretty sure the next problem says, what is the linear regression equation? What do the variables represent? And sketch the linear regression equation on the graph. I just did all of that right here. So I'm just going to copy and paste it into my chart. All right, so I go back to here, and I'm just going to paste it in here. Is it thinking about it still? Let's see. All right, I'm going to paste it unlinked, and there it is. All right, I'm going to make it a little smaller so it kind of fits on the problem right here. And we'll just cover up that old scatter plot and fix it with the new one. All right, so what is the linear regression equation? It's given right there. What do the variables represent? I do need to tell what the variables represent. The variables represent the, make sure I'm in there, the ticket sales and hot dogs. All right, sketch the regression equation of the line. We did that. All right, so the next question says, for a linear regression model, the value of the correlation coefficient R measures the strength of the association between ticket sales and hot dogs sold. The closer the value is to 1 or -1, the stronger the association. So now I've got to use my graphing calculator and do what I did on the last lesson. I'm going to hit Stat, Edit, and then I'm going to start typing in this data right here. So I'll move this over so I can see it. And I'll pause it while I put it all in. All right, so now the data is in the calculator. You hit Stat, arrow over to Calculate, and I want to go down to linear regression. So number 4. Hit Enter, 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 Enter. And again, my diagnostics keep getting taken off, so I have to go to second, 0, and arrow down until it gets to the diagnostics on. So I got to make sure I turn the diagnostics on, which is right here. Hit Enter, Enter again. Now I'm ready to calculate the data again. So 1, 2, 3, 4, and there is my R, 0.9866. 0.9866. So down here, you put 0.9866. This is not one of those numbers you need to round. You need to make it 0.9866. In fact, you could probably even go further, but 4 is okay. If you just put 0.9 or you round this to 1, then there's a lot of them that are going to 0.5 rounds to 1, but that doesn't mean the R value is very good. Since this is 0.986, that's really close to 1. So if you look, my data here should be really close to the line. It's pretty close. It's almost on the line. They're not all on the line. That's why it's not a perfect 1, but they're really close. Okay, so the last question down here. Based on the appearance of the graph, is there a positive, negative, or no correlation? First off, it's going uphill left to right, so that's positive. So we did that. So you write positive. Justify your response by describing the pattern. They go uphill left to right, so you write. They go uphill left to right. All right, on the next question, when the relationship between two variables is strong, the data points are tightly packed about the regression line. A moderate relationship means there's more scatter. A weak relationship means there is a linear pattern, but the data points are widely scattered. Does the relationship between the advanced ticket sales and the number of hot dogs sold appear to be strong, moderate, or weak? So if I'm looking at this one, they're pretty packed right along that line. So I'm going to say it's strong. So you write strong. Support your answer using the type of correlation, the scatter plot, which we've already done. So you would write strong, it's positive, and it's linear. Because there are some that are not linear. They may have a curve to it, some kind of curve to it or something like that. And that could make it quadratic. It could make it exponential. It could make it all kinds of different things. Okay. The next assignment that you do, some of the data that you're going to look at is going to be exponential and some of them are going to be linear, and you've got to decide which regression equation you need to give. All right. But on this one, they're linear. All right, so explain how the correlation coefficient confirms your answer in part E. Well, it was close to 1. That's it. That's your explaining. R was close to 1. All right, use the following options to complete the sentences. All right, so the slope of the regression line is. So if I go back up here, let's see. All right, so when the relationship between the two variables is strong, oh, we already answered that. Never mind. Let's see. Use the following. Okay, the slope of the regression line is. So we go back to our regression line right here, and the slope is 0.809. So I go back down here, and that's the answer. So right here, put 0.809. 0.809, which means that for every 1,000 advanced tickets sold, because it says it's for every 1,000, the regression model predicts an average. Now, is it an increase or a decrease? It was going up, so increase of hot dogs of 809 hot dogs sold. So the way it looks, if you look at 0.809, that is really 809 over 1,000. So that means for every 809 hot dogs, there was 1,000 tickets. Okay, so that's 0.809, that's 1,000, that's an increase and 809. In the context of the situation, does the y-intercept make sense? So let's go back and look at our y-intercept. The y-intercept says it is negative 4.12. So could I have a negative 4,000 hot dogs? So does it make sense? No. Why? You can't have negative 4,000 hot dogs. Okay? So if the advanced ticket sales are 56,000, approximately how many hot dogs would you expect to sell in the game? So I would take my calculator. I'll just go second mode, get you back to the home screen. And I'm putting in 56,000 tickets. Now, the reason we came up with this equation is so that we can figure out how many he needs to buy, how many hot dogs he needs to buy. So if there's 56,000 tickets, that's 56. So the equation was 0.809 times x. X is 56. So I put 56 right there. And then it was minus, what was the equation? Minus 4.12. So 4.12. So we get 41.184. So remember, this is for every 1,000 hot dogs. So really, he needs to buy 41,184 hot dogs. So if I go down here, yeah. So how many hot dogs should he expect to sell in the game? 41,184. Advanced ticket sales is not the only factor when determining the number of hot dogs sold at a game. What other variables might explain the association between advanced ticket sales and the number of hot dogs? So what else could make a game make the hot dogs go up. It could be maybe a game that is going through dinner time, so therefore more people are going to want a hot dog. It could be hot dog night where everything, all hot dogs are 50 cents or something like that. You're going to sell more hot dogs then. It um, could be raining. So there are just what other variables might explain the association between them. There are games to where other things could make a difference. Okay, so right here, Jorge is in charge of ordering hot dogs for the baseball game this weekend. Based on the information in Part J and the fact that Jorge knows there's an 80% chance of rain, do you think he should follow the model and order 41,200 hot dogs for the game? I'm going to say no, because not as many people will be at the game, even if they had advance tickets. So that's what you write and explain, because rain's going to make it to where not as many people show up. The table below shows the birth rate per 1,000 people in the United States, the variable year since 1940. What does the ordered pair 2023.7 mean? Well, it just means that the ordered pair, let's see, the 20, that's 20 years since 1940. So 20 plus 1940 is 1960. So we're talking about in 1960, the birth rate was 23.7 births for every 1,000 people. So per 1,000 people, there was 23.7 births. What year is represented by the year 40? Well, if this is 40, it's 40 years from 1940. So 40 plus 1940 is 1980. Construct a scatter plot for the data and label the axes. So we're going to go back to our spreadsheet, type in the data, and do it again. So I'll do that in just a second. Okay, so since it's just like the last one, it's the same thing. Go to your scatter plot, type in all this data. You may need to make a new one because we only highlighted this much data and there's more points to it. So you may just use another blank spreadsheet. You could use another blank spreadsheet and start over from scratch. Put the regression equation in there. I would go ahead and put the trend line, and it says, what is the linear regression? You can find that. What do the variables represent? The variables represent the year since 1940 and the birth rate in thousands. That's what they represent. All right, so down here on part E, it says the correlation coefficient R has a value of, put that in your calculator and see what it comes out to. So the correlation coefficient, so that's what this is. This word right here is the correlation coefficient, has a value of, so right here, put it in your calculator and see which one of these it is. It's got to be one of these two numbers, which means that there is a strong positive, no, this one is not positive. This one goes downhill. Strong negative linear relationship between the birth rate per 1,000 people and the, let's see, years since 1940. That's what it was. So the correlation coefficient R has a value of one of these two numbers, which means that there is a strong positive linear relationship between the birth rate per 1,000 people and the year since 1940. What do the slope and y-intercept represent in the context of the situation? Does the y-intercept seem reasonable? Say, like on the last problem, it didn't seem reasonable because it was negative and you couldn't have negative hot dogs. So does this one seem reasonable? So if you look at your equation that you came up with on the scatter plot before, yeah, it should be reasonable because it's positive. So, and then what does the slope represent? Well, the slope represents there's a decrease because the slope is negative of whatever you came up with for your slope per thousand people. And yes, the y-intercept could be reasonable. So, using the equation of the line that models the data, predict the birth rate for the year 2015. Well, for starters, 2015 is, let's see, 1940 to 2000 is 60 years, plus 15 is 75 years. So we're looking at 75 years for what I plug into my calculator. So remember, you plug it in just like we did this last one, only you put the new equation, which, like I said, is one of these two numbers, times 75, because 75 years is 2015, and then plus, because I already told you that the y-intercept was positive, put the y-intercept out there. Put it in the calculator, hit equal, and it spits out the answer. Okay? So use the x-intercept of the linear model is approximately this 140.632 and 0. What does the x-intercept represent in the context of the problem? Is the x-intercept reasonable? So we're talking about that the x-intercept in this problem is where where the birth rate is 0. Okay, so in the year 140 years from, so what is that, 2080? In the year 2080, there is going to be no kids born. So is that reasonable? Do we hope in the year 2080 that there's still kids being born? So is it reasonable? No, it's not. Okay. So number 3, a real estate agent must often determine the price of houses sold. One of the factors that helps determine the cost is of the house is its size, the number of square feet of living space in the house. The table gives the number of square feet in hundreds and the cost in thousands of dollars of houses that sold recently to a town. So here's another where we're probably going to have to put it in the calculator or in the spreadsheet. So interpret the meaning of 22,195. So that just means that a 2,200, so 2,200 square foot house should cost $195,000. That's what it means. Okay. What is the linear regression equation that models? What is the R value? And then explain the meaning of the R in the context of the situation. So you can, they don't ask for us to graph it. So you could just put it all in the calculator because the calculator does give you the regression equation. So if I was to look at, say, the first problem where we found the R, see, here's the R, but since here is the slope, and then here is the y-intercept. So the calculator gives you the regression equation. You would just have to put y equals 0.809x minus 4.12, which is what your spreadsheet gave you in the graph. So you could you don't have to do the spreadsheet and the calculator on this problem. You could just put all the data in the calculator. So if you go to stat edit and then clear it out, and then type in all the data again, you could just put it all in the calculator and it would tell you all of this answer. So in the context of the situation, what is the meaning of the slope and the y-intercept? It's for an increase of 100 square feet in living space. There's an approximate increase of, should be $8,700 in the cost of the house. And when the size of the house is equal to, let's see, and when the size of the house is equal to 0 square feet, which is the y-intercept, the model says that it's going to cost $4,625 because that's the y-intercept. Okay? So I pretty much just gave you the answer to that one. All right, so Maria is trying to convince her husband to buy a new house. She uses the linear regression equation model to determine that a 2,800 square foot house will cost $248,000. She tells her husband, "We can buy any 2,800 square foot house for $248,000. Is this true? Is it a valid or invalid statement?" Well, it depends on where you buy the house. You might be able to buy a 2,800 square foot house, say here, for $248,000. But if you go to California or Hawaii, it's not going to cost $248,000. A 2,800 square foot house is going to be about $1 million. So is it valid? No. And that's why. I just gave you the reason why. So Taylor Swift is going to buy a new weekend house in Beverly Hills. She wants a house with about 10,000 to 15,000 square feet. According to the model, what is the range that she should spend on the house? And then after looking at Beverly Hills, she discovers that the home prices are 5.3 to 6.8 million. Explain why the model is not good for predicting the value of Beverly Hills. So in Beverly Hills, everything's going to be more expensive. Okay? All right. Prior to 1993, the Leaning Tower of Pisa was leaning more and more each year. The data in the table gives the lean of the tower for years, 1975 to 1987. The lean is the distance in meters between where a point on the tower would be if the tower were vertical and its position on a particular date in the listed year. So in 1975, the lean of the tower was 2.9642 meters and is coded with the last three digits 642. So instead of typing 2.9642 and 2.9644, they just put 642. So